So, this is the module 2 lecture which will talk about FSI, fluid structure interaction. Then we will deal with the dynamics of detailed dynamic analysis of ocean structures. We will take up examples of different platforms and we will handle both the LHS and RHS of the equation of motion, that is we will derive the mass matrix, stiffness matrix and damping matrices of the given system. We will also talk about how to estimate f of t. Of course, we cannot solve this x of t because it needs a lot of iteration. So, we will use numerical solutions for this and we will show you the results from the research papers directly. Before we getting into understand how to do a dynamic analysis of offshore platforms directly, let us try to talk about in the design perspective what will be the influence on fluid structure interaction. So, actually if you look at the first module lectures where we are talking about different kinds of forces acting on structural systems, we have already said the wave force is one of the important contributor for offshore platforms, which is irregular and prescribed and random dynamic loading acting on the structure. There are many theories available in the literature to define the water particle kinematics, sea surface elevation, which varies with velocity, current, presence, etc. So, we can use different ideal equations to find out the velocity and acceleration of the water particle. Then we will also try to know how to get the forces, lateral forces exerted on the structural member by these wave interaction. But now I will talk about the design perspective on fluid structure interaction, where we will say that what are those important contributors when in a fluid flow a structural member remains in a fluid regime. So, what will be the interference effects on structural member on the fluid flow? We all know that as long as there is no obstruction by any member on any fluid or any domain, no force is exerted. For example, wind blows from left to right on this hall and there is no obstruction to the wind flow, wind will not exert any force. Wind or any lateral force will be exerted on a member only when there is an obstruction caused to the fluid flow. So, let us talk about what is that obstruction caused by the presence of member. If the member is vertical, if the member is horizontal, if the member is large diameter, if the member is fixed at the bottom, member is floating, what would be the interference effects of this, and how design perspective is important in fluid structure interaction, because it is important to know that what will be the forces arising from different position of the members under different category if we really wanted to know f of t in a given equation of motion. So, it is very clear to understand basically for hydrodynamic problems we all know that boundary conditions must be met. If you look at the boundary condition implementations on hydrodynamic problems, it will ultimately land up to what we call BVPs, which is classified as boundary value problems. Now, BVPs consist of differential equations and of course, a set of relevant boundary conditions which has got to be met to solve the boundary value problems. Now, we are bothered about this slide or this point onwards. Hydrodynamics actually causes vibration. The moment it causes vibration, it will result in a structural motion. The moment structure starts moving in the regime of fluid flow, there is an external action acting on the member. Now, this structure will be displaced, whether the structure is fixed, whether the structure is floating, compliant, there is always a displacement on the structural member, which is a result of the external force acting on this member, which arise essentially from the vibration caused by hydrodynamic effects. Now, we are not bothered about the boundary value effects, because the boundary value effects will only modify the characteristic of hydrodynamic forces. What we are bothered here is what is the influence of the structural displacement on the fluid domain. We are looking only this part of it. The moment a structure is displaced from its equilibrium position, we all know for a given design the structure will always try to recenter it itself. What does it mean is, when the structure is displaced from its equilibrium position, it is a natural tendency in a design the structure will try to come back to its normal position. Now, it cannot happen because the structure can regain its normal position only in the absence of external loads. Now, the external loads in offshore systems are continuously present, there is no absence case considered. Therefore, recentering will always be an oscillatory motion. This oscillation will again cause a secondary force in the medium itself. Now, there are two forces oscillated here. One, the external force caused by the fluid flow on the member, plus the result of the fluid flow which is causing displacement in the member, which invokes equilibrium movement on the member by recentering capability, which will induce a secondary motion which we call oscillation. So, there are displacements or causing vibrations and oscillations. There are two important categories of aspects dynamics present in FSI. Therefore, ultimately the structural member will continue to oscillate under the action of wave forces. Having said this, we must understand that fluid structure interaction plays a very important role for structures placed in the path of flowing fluid. The presence of structure significantly alters this flow field in its vicinity, that is very important. Now, depending upon the diameter of the member versus the wavelength effect, what we call d by L effect, etc., the significant alteration of the structure in the fluid field may not be present. So, what we mean to say is the structural presence is felt only within its vicinity. So, in the closed regime it is present. On the other hand, if you have got two members placed at a large distance or spaced at a large distance, the cascading effect of one on the other caused by the fluid medium may not be influential. So, spacing, d by L or the diameter versus wavelength, all are important factors now to understand that what will be the influence on the presence of structure in the fluid medium. Adding to it, the degree of compliance offered with the structure, because the degree of compliance is nothing but the support conditions given to the system by the external boundaries. For example, it can be floating and anchored to the seabed, it can be completely floating and controlled by a DPS system, can be rigidly fixed to the seabed, etc. So, what is the boundary effect you are giving to the structural system to avoid the degree of compliance or to induce a degree of compliance to the structural system adds further complexity, because this will create additional reaction forces to the excited force. Now, even though the structures remain flexible, for example, in TLP, in certain degrees of freedom, dynamics still become important, because it is not the deformation capacity that is looked upon, it is actually the vibration caused by the medium is looked upon. Therefore, fluid structure interaction becomes interesting and becomes vital for structures placed in the fluid medium, because it alters the steady flow. Steady flow may be in the form of current or a vertical shear, because it induces a vertical shear, it induces a displaced or differential pressure gradient between the upstream and downstream side, which we will see in the next slide. But in the real state, structures experience large oscillating forces in the flow direction. Now, there are two ways here. One is structures experience forces in the direction of flow medium, one is in the transverse direction. Now, when the structures are placed in the flowing fluid, flow pattern is significantly altered, restraints are developed in the fluid medium to maintain the position of the structure, because the moment you try to push the structure, structure will start exerting its boundary value limitations to the fluid medium itself. So, that will cause an additional reaction which will induce force on the medium back, and depending upon who is the winner, either the structure is affected or the fluid medium is altered. Ideally, flow may be considered as uniform with constant velocity in the region outside the vicinity, which we call technically in hydrodynamics as laminar flow, but flow with the change its direction when it encounters cylinder in its path. This will cause what is called flow separation. Now, the extent of flow separation in a given system strictly depends on incoming velocity. Therefore, water particle kinematics becomes very important. We will talk about this equation slightly later at the end of the lecture. So, water particle kinematics becomes very important, because extent of flow separation depends on that. One may ask me a question, what would be the influence on flow separation on the force exerted on the structure? Once the flow is separated, then they will act as independent medium, there is no interaction between the flow lines. So, the extent of flow separation depends on incoming velocity, lower the velocity, higher the drag coefficient. Now, the drag coefficient, which is called a CD, which is a very important item, which is now identically argued upon in the research front, which we call as drag crisis. I will talk about that slightly later in the next slide. So, drag coefficient is enhanced, inline forces will therefore become negligible. Now, cylinder will experience pressure which arise from this flow pattern, and therefore, it also increases or creates tangential pressure which arises from friction between the fluid medium and the cylinder surface. Now, the point of interest is here, the cylinder surface does not remain always smooth because of the marine growth deposits on the member. The moment the cylinder surface becomes rougher, it attracts more and more forces, and therefore, the drag and inertia coefficients keep on changing. Therefore, there is always a constant interaction between the structure, even though the structure does not move. Now, please understand, the structure is or the member is fixed to the bottom, it offers reaction, this reaction interferes with the fluid medium, and that alters the fluid flow actually. So, if you keep a member may be fixed or floating, it will alter the fluid medium. The moment the fluid medium is altered, it exerts forces, and this is a continuous process. And adding to this complexity, The member is also moving. In terms of compliant systems, you add more secondary vibrations introduced in the system, which you call as oscillatory motion. Therefore, forces acting on the structure in the fluid medium shall be classified as two. One is the drag and the lift forces. Drag is what we call inline force acting in the direction of flow. Lift is the transverse to the direction of flow. There are two ways here the flow will be characterizing the forces on the member. Further, the drag force can be classified as higher and smaller frequency components, which we call as springing and ringing responses later in the later part of explaining TLP for dynamic analysis. Therefore, both the frequency components are important, higher as well as smaller. These components will be of course functions of the geometry of the given system and the flow condition. Now, here the design becomes important. If we really wanted to make design interceptive force compatibility, in that case the geometry of the system plays a very important role. So, since the drag force is component of the function of the geometry, which is the design interception in the force calculations, if the geometry of the system is very large, it will invoke additional forces because of its size or the design itself. Now, interestingly, you will understand in any classical structural design, forces are estimated on the members and the members are designed for the given forces, whereas here you see the geometry induces forces on the system itself because of its interaction with the medium. The lift forces, which are transverse to the direction of flow, contain oscillatory components with multiple frequencies, which are also important. Now, you have a member which is vibrated or which is vibrating or which is displaced in the direction of flow because of the drag effect, which is also vibrating with multiple frequencies in the direction normal to the direction of flow, which is transverse motion. So, now the system or the member is interactive in both the components. Now, let us see what happens on the downstream side. Now, one can understand or ask a question, what do you mean by a downstream side? Let us say I have a member, let us say we have a cylindrical member, maybe of a specific diameter d. The wave is approaching the system in this direction and the wave leaves the platform or the member in this manner. We are hypothetically considering a unidirectional wave. Of course, we know that the direction of wave is not unidirectional, it is multidirectional. Hypothetically, for laminar flow, let us say it is a unidirectional wave, we call this as upstream side, this as downstream side for a unidirectional flow. Now, on the downstream side, flow will return to its unaltered condition because it leaves the member and then becomes unaltered after a specific distance. This is due to the fluid viscosity and the damping effect present in the medium. Now, the region of altered flow directly behind the structure is what we call as wake region. This is very important because this will cause asymmetric pressure distribution in the inline direction of forces. This results in net horizontal force in the inline direction. In the wake regions, there will be one-to-one relationship between the extent of wake region and the restrained loads, which means that fluid structure interaction in the wake region is becoming determinant. You can calculate this very in the closed form solution. Frequency content of the wake region is say same as that of the restrained loads. So, on the other hand, you see here the frequency content of the force component remains and assimilates a similar value as that of the restrained loads. It means you will see that the wake region invoked forces are in resonance with that of the restrained loads. So, this induces, though in a multiple frequency, a kind of an additional force on the wake region, which is on the downstream side only for a specific sector, beyond which the flow becomes unaltered back again. So, it is not only the flow direction important inline, it is not only the transverse direction, it is also the downstream side sector which is disturbing the flow medium, which causes forces on the member. Now, one can ask me a question, I want to reduce the effect of flow separation, what should I do? To reduce the effect of flow separation, in design people used to adopt shape of the member as one of the important parameter to streamline the flow. Now, one can ask me a question, what are the factors which influences this parameter in a two-dimensional frame? Fluid density, steady uniform flow velocity and the frontal area of the member encountering the flow. So, which is given by this equation, where rho of course is sea water density, CD is the drag coefficient, A is the frontal area of the member and U is the uniform steady uniform flow velocity. If you look at the flow regimes in uniform flow, let us consider axis of cylinder normal to the flow direction. Flow is without turbulence and boundary effects. Now, when you talk about this in aerodynamics, people generally look at one important parameter which we call as Reynolds number, which is indicated as RE here. depending upon the range of the Reynolds number, one classifies the flow conditions and assimilates what are the kinds of forces which can come on the cylinder. For example, if the flow region remains laminar and steady, for which the verification is the Reynolds number should lie between 0 and 40, the flow condition shows there is no separation of flow. If there is no separation of flow, the drag forces occurring in the direction of flow will be a predominant force acting on the cylinder. On the other hand, if the flow becomes subcritical, which can be verified with Reynolds number ranging from 40 to 510 power 5, you will see that there are broken streamlines generated in the flow field, which induces lift forces, which also of course depends on Stokehal's number. The steady drag force plus small oscillating drag forces at double the frequency of lift force will be now acting on the structure. When the flow becomes supercritical, where the Reynolds number ranges from 510 power 5 to 710 power 5, then it will develop what we call ill-defined vortices. The drag forces decrease rapidly in this situation, lift and drag forces will be seen at higher frequencies now. Now there is an extreme shift of the frequency from the direction of regular to that of small frequency to that of double of the frequency lift force to that of the higher frequency. Now one can see here, depending upon the flow field and flow condition, you will see that all components of the drag forces in lower and higher frequencies and double the frequency are also present in the given system. If the flow becomes further transcritical, where the Reynolds number exceeds 710 e power 5, in that case vortices will be present. The flow will become turbulent due to randomness in fluid viscosity, which results in subcritical range as the top you see here. So lift forces will be again created. So depending upon the flow field mannerism, forces are induced in the member when the member interferes with the flow field. There is something called drag crisis in the literature, which is very important for drag dominant structures in offshore platforms. At critical flow, for example, Reynolds number exceeds 2 e power 5, then the drag coefficient decreases phenomenally. This also causes the wake to become very narrow. When the wake becomes narrow, this causes a decrease in pressure gradient. This decrease in pressure gradient will result in sharp drop in the drag coefficient. This is what we call as drag crisis. The drag crisis is less for of course rough cylinders. Therefore, as per the design, people induce roughness in the cylinder surface. That is why you will see there are perforated members, or there are stampered members, or there are stripes placed on the members which will induce surface roughness, which will decrease or the drag coefficient in the given system, which is one of the design methodology for doing this. But greater the roughness, the separation of the flow is earlier. When the flow gets separated, you will have the lift forces induced in the system automatically. So one benefit creates one more demerit in the given system. So this will result in pressure difference between upstream and downstream forces in the member. Since the pressure distribution is not symmetric about the flow direction, this will now generate additional forces, what we call lift forces, which is given by the equation on the slide now, where CL is the lift coefficient, and of course A, rho and U are as same as defined in the previous slide. Now when you talk about oscillating cylinders which are not fixed to the seabed, there are three kinds of force generated. One is what we call inline forces, what otherwise we call as drag force, given by the equation available here. Other is the inertia force on the cylinder, given by the equation available here again, Fi and Fd. Now the total force in a given system, the right hand side of equation of motion, the summation of the drag force per unit length of the system plus inertia force per unit length of the system plus of course the mass of the platform into acceleration of the structural system itself. Now there are two components here, please understand. Fd and Fi have of course the velocity and acceleration components which arise from the flow field, and this acceleration component is from the structural system because structure is now oscillating. So there are two components inherently present in the system, one because structural motion itself, one because of the oscillatory motion induced by the interference of the system on the flow field. So now it is very interesting to know all of us that f of d is dimension protected by having one of the system modular here, so that it can also cause reverse effects. Now we will talk about what we call forced oscillation, which slowly depends on Reynolds number and Killick-Carpenter number, but interestingly in design of offshore structures people neither look at this number independently, but they look at the ratio of this number which we call Stokes viscous parameter, which is ratio of Re to Kc. This is actually used in the design instead of simple Reynolds number. Now the total force, as we saw in the last slide, is the inertia force arising from the system plus drag force arising from the system plus mass into acceleration of the system itself. So, these two are from the medium, this is from the structural component. Of course, when the structural component does not move, this component becomes inefficient. Of course, this will be anyway present in the given system. Therefore, the right hand side of equation of motion in a given dynamic system of motion structures will never be set to 0. So, if inertia force is maximum, interestingly drag component will be negligible and becomes vice versa. That is what is seen in the research, in the literature. Now, let us talk about vertical cylinders in uniform flow. Vertical cylinders experience different kind of loading from the flowing fluid. Fluid structure interaction will be defined by Reynolds number for cylinders with infinitely long, smooth and fixed at the bottom. The cylinder roughness and fluid turbulence reduce boundary value on either side of the subcritical region. If of course, the length of the cylinder is finite, this will introduce 3-dimensional aspect to the flow field. Ends of the cylinder will of course have significant effect on the drag and lift coefficients because they are considered to be covered in the original design. They are also location dependent of the cylinder. Therefore, the coordinate of the cylinder or the coordinate of the CG of the cylinder with respect to the fixed boundary plays an important role to estimate these kinds of forces on the given system. Vortex shedding pattern will also be altered depending upon the flow field surrounding the vertical cylinder. Like in the case of horizontal cylinders, reduced velocity can also be seen for different ranges. For different flow regions categorically 1, 2 and 3 has given by Hampshire and Walker in 1987. The reduced velocity ranges from 1.7 to that of 8.0, which causes vortex shedding effect. In the case of 1.7 to 2.3, where the flow regime is calculated as classical value 1 as given by Hampshire and Walker, the vortex shedding becomes symmetric, which will result in inline oscillations only. Please understand, when you talk about design of a given system, we must understand what frequency we must approach for calculating the response of the system. So, when your flow regime is only with a reduced velocity of 1.7 to 2.3, which causes symmetric shedding, it will result only in inline oscillation, whereas in flow regime 3, where the reduced velocity can go as high as 8.0, it causes alternate shedding of vortices, which will cause transverse vibration, and inline vibrations are seen at frequency twice that of transverse vibration, which will result in what we call figure 8 motion of the structural system. So, here the stability of the system will be challenged. When we move on to shallow, medium to deep waters, then the flow field slightly gets altered. In deep waters, the flow is not uniform with the depth, it varies. We all know that because the water particle velocity and acceleration keeps on changing with respect to depth. It is maximum at the mean sea and it is practically 0 when it goes to the seabed. Positive shear will be generated. Now, interestingly, shear is always a force which tries to divide the member in its characteristical strength. So, positive shear will be seen. I will show you in the next slide how the shear is generated. Velocity will become greater than the near the surface. When the vertical cylinder is in the shear flow condition, a 3D flow regime will now occur. Now, let us quickly see under positive shear the wake region. We all know the wake region is the flow past the cylinder. If this is my cylinder placed in the flow regime, if this is my elevation and this is my flow direction, we all know the wake region is on the flow past cylinder here. Under positive shear, the wake region experiences vertical upward flow. It will try to lift the member. You see here, there is a downward flow induced along the stagnation line in the upstream side, whereas in the downstream side it is going to create an upward induced flow in the wake region. This will result in what we call as a sheared motion between the upstream and downstream. There is downward flow on the upstream side and upward flow on the downstream side, which will cause a shear effect on the given member in the wake region. This shear flow effect reduces the pressure coefficient at the top of the cylinder and of course increases the coefficient at the bottom. Usually it is vice versa when this effect is absent. Coefficient also changes with the strength of the shear value. In uniform flow, the vertical cylinder will show vortices at the same frequency over its entire length. It means the entire member will now become critical. In shear flow, frequency changes continuously, therefore it can enter and exit the resonance domain of the member very frequently, which results in what we call fatigue damage to the members. When you now place the cylinder horizontally, for example, pontoon members in a uniform flow like subsea pipelines pontoon members, members of floating breakwaters, etc. In such cases, these members will be influenced by the current and the waves together. Under uniform flow field, horizontal cylinder will generate waves near the upper boundary, what we call as free surface effects. In such situation, wave resistance purely depends on the Reynolds number as given in the equation here, where y1 is the depth of immersion of the member measured from the axis of the cylinder to the free surface. When this member or this value exceeds the radius of the member, the maximum wave resistance will occur, and the minimum when Fr is less than 0.375 as seen in the literature. Now, the boundary effects and end effects of the cylinder introduces 3D effects in the flow past cylinder in the entire length of the member, which result in major difference between the horizontal and vertical cylinder is the appearance of the lift force. When the horizontal cylinder is located near the boundary, flow will become unsymmetric. Lift forces will become a function of the cylinder diameter and distance to that of the boundary from the axis of the member. Horizontal cylinders will also be subjected to flow induced vibrations, which will cause secondary oscillation to the given system. Horizontal cylinders like vertical are also subjected to shear flow. Under shear flow, the velocity variation across face of the structure will become significant. Ratio of turbulence to velocity variation across the cylinder is higher than that of a vertical cylinder. So, therefore, now you see in a given system like a TLP, where there are column members and pontoon members, one kind of member is having different kinds of shear flow compared to the other. It means the member has got a disagreement in the pressure variation, the upstream and downstream side, whether the member is oriented vertically or horizontally. For increase in shear parameter, Stokes number therefore increases. Now, when the Stokes number increases, this will result in vortex reduced frequency, which will cause secondary vibration to the horizontal members. With a fixed horizontal cylinder, load at a given velocity for a positive shear is generally seen more for an uniform flow. At a free surface, the vertical load in both positive and negative shear increases significantly in comparison to the uniform flow. The dynamic vertical loads on the cylinder mid depth under positive and negative shear contain higher energy at higher frequencies. So, therefore, the nearer the surface, this effect is significantly reduced. Horizontal cylinder therefore, at free surface suppress eddy shedding effects and wake formation is not seen for the members at the free surface. The steady component of the vertical load increases significantly for the horizontal cylinder at the free surface. So, there are two types of components. One is the vertical component, which is called the lift component. Other is the horizontal component, inline force, which is called drag component. So, depending upon the orientation of the member, how do you place the member y1 from the free surface effect, you will have the difference in these kind of loads also created in the given member. More interestingly, you also have something called blockage factor. Now, with this blockage factor becomes significant when you got closely spaced members. When the closely spaced members connected in different orientation, this causes distortion in the fluid field around it. For closely spaced members, the structure is considered to be dense. For a dense structure in literature, flow field slows down as it travels through the structure. When the flow field slows down, this is what we call as blockage effect. This complicates the actual velocity field around the structure. Velocity is reduced, but the force increases. Now, let us coming back to the point of the load on the structure increases due to this blockage effect, which is given by this equation, where CBF is given by the blockage factor, which is given by this equation, or in case of group of vertical cylinders present in the flow field, you can also calculate CBF using this relationship, where S is the center to center distance of the cylinder and where D is the diameter of the cylinder. When we talk about wave structure interaction, it is very important to know that when the waves pass the cylinder, it causes oscillating inline forces on the cylinder. In addition to that, the free surface also changes in case of submerged cylinder because of the variable buoyancy or variable submergence effects. Large structures placed in wave field alters incident waves in its vicinity itself. If the dimension of the structure is too large compared to the wavelength, flow remains attached to the structure. So, the flow remains attached means when the flow is from left to right, it has a tendency to take back the structure along the same direction. Therefore, the resistance offered to the structure will become null and void. Of course, the important components present in the structure in this lecture are given by these references as you see here, which include some of the important components as we discussed. In the design perspective given by me and Bhattacharya, given by me in two of the recent books in Springer and CRC Press, which will be now coming up. So, now adding to having a summary of the forces which act on the cylinder, we will give you some important non-dimensional numbers and some of the important effects of these forces in a summary as a table now. So, let us talk about some of the important symbols and forces used in terms of relationships. Let us say Reynolds number, which is given by Fr, which is ratio of inertia to gravity. The equation of course of Fr, we all know that u0 square by Gd next one is of course the Reynolds number, given by Re. We have already seen the influence of Reynolds number in the given system. Is ratio of inertia to viscous force. Given by the relationship u0 d by nu. I will talk about these constants slightly later. Next is important is an Euler number, given by Eu, ratio of inertia to pressure. Cauchy number, Ch, inertia to elastic, Killigan-Carpenter number, Kc, drag to inertia, Stokes number, given by St, by u naught, where d diameter of the member, u naught flow velocity. Out of this, let us talk about these three numbers which are important for us. One is the Cauchy's number, or the Stokes number, Euler's number. Talk about Cauchy's number. It is used to measure deformation in shape caused due to fluid loading. Stokes number is an index of non-dimensional vortex shedding frequency. Euler's number used to measure stresses on the structural components under pressure load. In dynamic analysis of offshore platforms, you will normally come across lot of non-dimensional variables. Let us look at the summary of non-dimensional variables. Which is important for us to understand because they will have some important role to play. Frequency ratio, which is actually oscillating frequency to structural frequency. Other is called aspect ratio, which is a design parameter, which is RA, which is L over D, L length of the cylinder and D dia of the cylinder. So, geometric parameter. The other one is roughness parameter, which is given as Ks, is given by K by D, I think is small k, where small k is called surface roughness, and of course D is the diameter. Something called reduced velocity, which we talked about in the presentation recently, which we call as VR, which is given by U by Fn D, where Fn is the natural frequency of the structure, Ry called free amplitude ratio, which is given by Y0 by D, amplitude of free oscillation. You will obviously see most of the cases in these non-dimensional variables are connecting the behavior of the flow field to that of the diameter. That is why they are called design parameters also, okay, because most of them are connected to the diameter, you see. Elevation ratio, which is Re. Of course, this may get confused with the Reynolds number, Y by L, where Y is the elevation of the point from the free surface. Turbulence intensity, u developed by u, where u developed is a derivative of the velocity from mean velocity. Drag coefficient Fi by half rho u square d, we already saw the equation earlier. Lift coefficient Fl by half rho u square d. Velocity gradient indicated by epsilon, which is um by u minus 1, where um is the maximum velocity. Surface effect coefficient which is given as Cs is given by y1 by d, where y1 is the vertical distance of the cylinder axis from the free surface. Bottom effect coefficient Cb, which is given by y2 by d, where y2 the vertical distance from the cylindrical axis to the bottom boundary. So, as a summary of this lecture, arising from FSI, fixed cylinder in waves will develop or experience forces which is given by dF, the elemental force on unit incremental length of the member, Cm rho pi d square by 4, flexible cylinders in waves will experience forces okay. where the term V, or let us say x, please make it Tx. The term x relates to structural constant, maybe velocity and acceleration respectively, whereas the term u refers to water particle. Now, in design one is interested to know what is the maximum force coming on the member, Fd max, which is Cd T by 8. Similarly, inertia force maximum experienced by the member the small d indicates water depth. Of course, the capital D indicates diameter of the member. Maximum wave steepness is given by h by L 0.14 tan hyperbolic kd, where of course k is the wave number which is given by 2 pi by L, where L is the wavelength and so on. So, this will be a thumb rule for you to just glossary of terms looking at different non-dimensional variables which are oftenly seen in the right hand side of the equation of motion when you are solving for the different kinds of forces. People use this terminology, so one must know how to compute them and what is the influence on different kinds of numbers, the variations and the participation when a fluid medium is interfered by a member depending upon its orientation, vertical, horizontal, fixed, floating, etc. Just now we have seen this lecture. So, this lecture summarizes the fluid structure and wave structure interaction in terms of brief understanding how the forces can be estimated on the members. Thank you.